Welcome to the CEAT Research Seminar Series, Virtual Edition.
Our next speaker is Dr. Ekin. He received his PhD in electrical and computer engineering from Texas A&M in 2012. He joined OSU in the School of Electrical and Computer Engineering in 2016. He has 4 years of industrial experience while he was at Qualcomm as a senior modem systems engineer with the Department of Qualcomm Mobile Computing. At Qualcomm, he received numerous QualStar awards for his achievements and contributions on cellular modem receiver design. His research interests include the design and performance analysis of wireless systems in both theoretical and practical points of view, visible light sensing, communications and applications, non-contact health monitoring, and Internet of Things applications. Sabit, it's all yours.
Thank you. I appreciate it, Dr. Ponting. You guys can see my screen, right? Steam. Awesome. So thanks a lot for the opportunity, Dr. Ponting, and thanks everyone for attending. So today I will be talking for some of our current projects in the areas of the wireless communication and the sensing projects. So I'm director of the OSU Wireless Lab, and I'm also founding member of the Twister as an interdisciplinary research team, as most of the members are from EC and the physics. And I'm also team members of the USRI Rural Renewal Initiative and the REPTAS Lab. All right, so part one will be the wireless communication and part two will be the wireless sensing. So the first project is the hybrid RF optical communication architecture for the LUNARCOM, lunar missions. And the objective is basically connecting the Earth and the Moon. So as some of you might have already heard, NASA plans to go to the Mars, send a human to the Mars. But prior to that, we need to practice, we need to learn how to live in the deep space, how to operate in the deep space, actually, technically. And the first target is going to the Moon. So for the next 4 to 5 years and last few years, starting from last few years, the primary objective is all the missions are really focusing on going to the Mars. And the objective is sending the next man and the first woman to the Mars. And the plan called Artemis plan. And as part of this plan, they are planning to build a gateway. A gateway is going to be very similar to ISS. This is one of the pictures showing the picture of ISS. ISS is basically orbiting the Earth, and the gateway will be orbiting the Moon. It's going to be similar idea. So astronauts will be going there, living there, and they will be going to the Moon and collecting the samples and doing their experiments and coming back. And as part of this plan, actually last week, the NASA has awarded Nokia to build the 4G communication network on the Moon. So the target completion day is 2028. Okay, what is the challenge here? Is to transmitting, highly increasing the data, scientific data from Moon and even eventually from Mars and Earth. How we can change the data between these two endpoints. So what we propose to know, we are closely working with the NASA Goddard Flight Space Center. And based on our interaction, there are two ways of communicating and sending data from one point to another, either using the light, which is laser basically, or the other option is using radio frequencies. These are both really the highly efficient communication methods, and these are the only two methods actually we have it. So how we can do is this. The RF methods are really providing stable communication links, and they don't have any impact on the weather, but they're providing low data rate. But the optical ones, they're providing really high data rate, the laser beams, but they're having the cloud issue and they are especially requiring very nice pointing because it's very narrow beam widths. This is the picture of showing for the radio waves and laser waves. So what we propose is, we're actually awarded and we started working on it, the combining best of these both worlds, RF and optical communication, and we call it hybrid RF optical lunar communication architecture. The idea is to collect the data from moon to the gateway, and basically we'll be relaying from the lunar gateway to the constellation of the LEO satellites. The companies like SpaceX and Iridium, they have already started to build their LEO satellite constellations, hundreds of them. And the idea is they will be able to really doing the hybrid optical communication, RF optical communication. The data from gateway will come to these satellites, small satellites, hundreds of them. And if there is cloud, we will be relaying, which is fine. But it's going to be kind of an ad hoc network. We will be able to send the data from one to another. And eventually, the ultimate goal is really to send to the Earth station and the NASA space centers. So this is pretty much the overview of the project that we're trying to work. This is the two initial designs that we have. One of them is showing the moon view. It's basically from the gateway and between the Earth. And this is the Earth view, actually the same setup, showing the constellation of the small satellites orbiting around the Earth. And the data will be relayed thanks to these satellites. And the objective is to create a robust and high data rate communication links for the lunar mission. Well, this is the multi-institutional project. We work with the University of Oklahoma, University of Tulsa, and the lead institution is the OSU and the Rasa Goddard Space Flight Center. And in OSU, we have the ECE, Electrical and Computer Engineering, and MAE, Mechanical and Aerospace Engineering. So as part of this project, we have an outreach activity, actually. The objective is to create a CubeSat program. For some of you who never heard about the CubeSat, it's basically a spread-size small satellite. It's basically, this is showing really nice picture of it. This is 1 cubic unit. It's called 1U. If you have two of them, you can put it together. It's going to be 2, 3, or 4 cubic units. These are being used when we don't really have. They're being used for specific purposes. Only one objectives, and they are being used for the cases where we don't have really a good justification for using a larger satellites. So this is the map, is a recent map. I got it from NASA website showing the CubeSat initiatives for the states. And these numbers are showing the number of satellites they have launched. Only 9 states don't have the CubeSat program. And unfortunately, we are one of them. So our objectives will be really, ultimate goal is to change this map. So we don't want to have that as said emoji here. And hopefully in next few years, ultimate goal is to put 1 CubeSat over there. So then the part of the wireless communication, I will be talking about the 5G, 6G, and beyond wireless communication projects we are working. Just a little bit of background. Okay, how do we communicate in wireless communication system? We use radio frequencies. All right, this is the whole electromagnetic spectrum is showing to us. This is really the sweet spot that we use to communicate most of our communication system. Actually, almost, I will say 90% of wireless communication system we are using are sub-6, less than 5 gig. Those can be your Bluetooth, Wi-Fi, satellite, cell phones, near field communications, AM radio, FM radio, GPS, everything is sub-6. We use higher frequencies also, mostly 5G start to use it. Actually, the recent iPhone 12 has this. It's using 30 gig and even 27 gig and 37 gig for the communication system. But those are mostly will be for line of sight, although it's providing really huge data rates, 5 gigabits per second of the data rate. So this is really important, and we have very little part of the spectrum that we can use it for a little bit long distance communication system. So we want to use it as efficiently as possible. This is the allocation of the United States from 0 hertz to the 300 gig. It's basically this part of the frequency. I think not much to say in here. It's super crowded, and these are mostly allocated by FCC, Federal Communication Consortium. Almost all the devices that you have, you will see FCC tag behind them or somewhere where they use the RF communication system. So in short, we have very little part of the electromagnetic spectrum using for wireless communication, and we want to increase this efficiency. Okay, let's have a little bit math. To send the data from point A to point B, you will have your signal being transmitted from transmitter going to receiver. What happened to your signal? The signal passed through the air, which we call channel. And the channel, electromagnetic, basically the channel will basically impact your signal. It's gonna reduce its amplitude, it's gonna do the phase shift, it's gonna do multiple things to it. But on top of it, we will have the noise as well. Any electronic system will have the thermal noise in simple cases. And this noise, you can put really interference also as part of this noise. In short, a received signals will be your original signal impacted with the channel and part of noise and interference. So this is only a question that I will have in my slides, and really, if there is anything I want to take away, will be this expression. I'm not sure if any of you have heard about the Shannon. We communication engineers, we believe he is as important person as Nikola Tesla. He is the father of information theory, and he's the father of the bits that we are using. Without him, I wouldn't be really doing this presentation right now. So he, in 1948, he found the expression with him given the bandwidth, which is here, V here, and signal to noise ratio. This is basically your signal inequality. How can you get your capacity expression? And look at the units, beats per second. We use it in every day of our life. And this capacity expression is really the limit. All the communication systems we are using right now will be below this limit. So Claude Shannon found it within the given bandwidth and the signal quality. He said, this is the best you can do for this communication system. And this is the limit that we can achieve. All right, let's take the bandwidth on this side of the expression, but we will have it. We will have bits per second per hertz, right? Because bandwidth unit is hertz. This is called spectral efficiency. 5G, 6G, all future ones, you will see this term a lot. Even in advertisement, they will say, hey, we have better spectral efficiency. Yes, what does that mean? Increasing the data rate within given the bandwidth. This is the wiki terms. All right, so we have, this is the cellular communication system, but it's really can be nicely related to the Wi-Fi as well. The objective in the newer communication systems are this: increasing the data rate, reducing the latency, and making sure the user is happy, and reducing the cost as well. And to do all this, we all have is really a fixed frequency, and we want to make sure we increase the efficiency of it. This is the 5G, and this is the data it is showing you. The recent measurements, I think in Qualcomm and the Verizon together, they show that in 5G, you can achieve 5 gigabits per second of the data rate. This is huge. Imagine that the fiber optic cable you are getting at your office is 1 gigabits per second. So one more thing I was going to show in this, the channel and the spectral efficiency, these two terms are super critical in a communication system. We want to know what happened to our signal. No matter what frequency I'm using it, I want to learn it, because if frequency, the behavior of the signals traveling in the air is going to be different in different parts of the spectrum. And I want to see what's happening with the spectral efficiency. All right, this is the second year of the project. Actually, we're working. This is the conventional network. You have your cells, you have your users, they are fixed, and users are mobile, but the base stations are fixed. So the operator will come and put the base station saying, hey, this is gonna be here. The more user I have, I might put more base station and expand it. That's good. But when a user is not there, that base station is still active. And this is really, there is a very nice trade-off between the two terms, spectral efficiency and energy efficiency. Like the agencies like DOE and NSF, they care a lot about energy efficiency as well. Yes, we want to increase spectral efficiency, but we don't want to decrease the energy efficiency. It's a trade-off between them. What we propose is here, finding that really sweet spot and really trying to improve it simultaneously, both of them. We are not going to go with a conventional traditional network. We will do with this proposed SPIDERNET. What is SPIDERNET? Is spectrally efficient and energy efficient network. It will be, the base stations will be operating only if the users are there. If the users are not, we can turn it off. Okay, you might say there was only still one user, not many users, that's still fine. We can increase the coverage of the other user, the other base station. That way we can increase the spectral energy efficiency at the same time. So we, in technical terms, we increase the degrees of freedom that we can play in the network design. This is one part, this is spectral energy and energy efficiency. If you remember here, I said the channel is super important. Different part of the spectrum will treat your signal differently. So we want to see what happened to our channel as well. One project that we are working with MAE and our other professors and ECE is to see what happened to our channel in millimeter wave channels actually, and even terahertz channel for UAV assisted communication. UAV assisted communication is coming and we will be using it, and it's very good for very largely crowded events, for the disaster areas. So the UAVs basically will be carrying the base station and providing the coverage for that area. But if you use the higher frequency, the motion from the UAV and the hovering can impact your communication system. Here's what we are doing. We use our robotic arm to mimic the motion of the drone, and we want to see how the channel will be impacted. We work on terahertz frequencies as well. We want to see how the terahertz channel will get impacted for similar scenario, even for different environments. So basically this part of the work we are using is the channel, and this part of work that we are doing is the spectral efficiency. The IoT, we have few IoT projects as part of the wireless communication projects. The first one is we work with the BAE, Biosystems and Agricultural Engineering, and the MAE and the ECE, three departments working together. The idea is this: the farmers, they don't want any sensors, anything to be above the soil. It's basically interfering with their farming practices. So the solution is to put your sensors under the ground. These sensors can be the temperate soil, like temperature sensor, moisture sensor, can be a lot of other sensors you can put it under the soil. But the problem is this: when you put under the ground, the radio frequency signals doesn't go far. The solution to this, putting a lot of base stations on the far and the field, which is not really good. So what we propose is to put the base station in the drone and let the drone go autonomously collect all the data, get closer to these soil sensors. What we are trying to do in this research to see what will be, basically this is a proof of concept, and we want to see if we can see what distances will be D1 and D2, how they will change for different moisture conditions, the soil moisture conditions and soil types. All right, livestock monitoring. So we had done soil monitoring, and now we have livestock monitoring. This has been there for a few years, and we are working with the animal science, agriculture, and EC. And the idea is this: making a tag like a Fitbit for cows. Put it in their ear, get their motion, get their location, and from that motion, we can get a lot of other informations. Ultimate goal is really in the future, if you can make it some in vivo sensors, we'll be communicating with this main tag, and the main tag will be sending to IoT base station and there from the users. These are some of our initial tags. Maybe you can see my camera is actually, there's one of them in my office, we have it. So these are the 3 cows, we already put the tags on them, we basically located. These are solar powered and they can go for months. Farmers, when we work with them in Elson, they don't want to change this one every other day, every week. They want it to be there for many years, many months. Years will be hard, at least depending how much data you send. And the reason we say IoT, IoT is low-powered, long-range communication systems. This is the big diagram is showing what we're going to do with livestock monitoring. We're going to check the health, productivity, location of the animal for the untapped land management, because you want to know where are your livestock most of the time during the day, which part, if you have different type of the grass, which part they are getting it more. So this can be a good land management strategy and data processing. The system model will be energy harvesting, we will be networking, and the sensors. So I won't really have time to go through all these details. Okay, the last part of the IoT is the using TV white space to bridge the digital divide. For those of you who haven't heard about the digital divide is a term that refers to the gaps in access to the information and the communication technology, ICT. This is by OECD terms. So this is the map showing the gap between the household in rural and urban areas. As you can see, unfortunately, Oklahoma is mostly in the average and below average. What does that mean? Rural people, they don't have access to the high-speed internet access. Doesn't have to be rural people. In a lot of rural fields and areas also, they don't have it. And 1 in 4, basically a quarter of the nation doesn't have broadband internet access. And unfortunately, COVID has intensified this digital divide more. As the students are online, digital divide grows greater. And it becomes really an emergency now. So what we are proposing is this: TV channels are being broadcasted using radio frequency systems. And these radio frequencies are not being used across all the in different positions across the whole US. Let's say this is the showing the spectrum map. Let's say we have around 45 channels, TV channels. And this map is showing in these TV channels, if it's not being used, called free channels or called white space. This is map showing how really the rural areas, most of the channels are not being used at all. These are fixed allocated. FCC give to these TV channels, but they are not using in that area. Then the question is, why not using this for communication purposes? That's how the TV white space came. And Microsoft is heavily supporting small startup companies to use this. FCC allows small startup companies to make devices to go use these free spectrums. If it's not being used by that TV channels, go ahead and use it for communication system. This is our idea. The other part is this: these TV channels are around 300 megahertz to 800 megahertz channels. These are UHF channels. These are super valuable channels. And we can use it for long-term, long-distance, non-line of sight communication system. All right, so we have started. This is being funded by the OSU VPR office as part of Tier 1 initiative. And this is the our team showing. So this big tower is a OSU feed mill. We put one of the base station on top of it. And these are our Yagi antennas. We went different location across the town and we did the measurements. This is for uplink and this is for downlink. Just one example, we have it here. From the base station to our client, this is 5 miles. We can achieve 14 and above Mbps data rate. This is huge. This is much higher than the cellular coverage and this much higher data rate. So we got initial results. What we will do next is go to Oklahoma, Tillman County. There's a farm over there and we'll be deploying this base station there. We want to see how it's impacting their life. They are using livestock auctioning, and they have their kids' education. We want to see how it's impacting their life. We will be looking at the communication perspective, but our other team members will be looking at other perspectives, the impact for this high-speed internet. So this is another project. We're working with the PIs, Dr. West, and we're working with Dr. Jacob. Just for the airplanes, in order for them to find the runway, even in the middle of the night, they don't see anything over there. The main way for them is really looking at these needles in their monitor. How this needle works, they basically get the received signals broadcasted or transmitted in the runway. We have 2 antennas. One of them is at the end of the runway, which is here. And there's another one, it's called glide slope, is on the side. These 2 are sending data horizontally and vertically based on the signal strength you receive. If you are getting the peak signal strength, you will be in the middle of it on the beam. But if you are on either side of it, your signal strength will be lower. In simple terms, you will be getting lower signal. So maintenance and inspection of these transmitters are super critical. It has to be properly maintained. And the current FAA is using those big, large aircraft for the maintenance and inspection of this. We are trying to see how we can really do something similar, of course, not to replace it, maybe augment the current system by using a drone. But drone, we cannot put a big receiver on it. You have to put a small receiver we call ultra lightweight. We designed a software-defined radio receiver and we put on the drone and we went to take measurements. One of the challenge we have seen is this: the propeller on the drone, they have higher RPM. They can really impact our received signal. This is one of the research work that we are continuing working on. So quickly, I have a few projects for the lightweight sensing. So to wirelessly sense, the two methods, some two well-known methods are using radar and using the cameras. So what we are doing here, we're using light, but we are not using laser light. We are using incoherent LED lights. These are low cost, cheapest, and everywhere. This is really a big overview for what we are trying to do. This is the signal we are transmitting, it's light signal. And as the light is hitting to the subject and from the reflections, the first one, we are trying to get the glucose level. The second one, from the chest, we're getting the heart and the respiration rate. And the third one, we are trying to get the gesture of the person. What is the benefit of this? It is safe, it's low cost, it's largely deployable. The cost of a device like this to building it, especially for the gesture and heart rate especially, it can be really $5 to $10. It's really local and it's very safe. So, and of course, as the data get being collected, this data has to be processed and we get the sensing. But the first one is has been recently funded by NSF, is the respiration and the heart rate, the middle one. As the light is reflecting from the reflections, we get the respiration and heart rate, and these are our measurements, as published results. It is showing when we send one of our students, go around for 15 minutes and come back, sit, and we put contact-based device on him to have a ground truth. And we compare with our measurements method, actually, light-based sensing-based methods. We are nicely able to get both heart rate and the respiration within 1 meter of the distance without putting anything on the person. And we wirelessly get the respiration heart rate. So as part of this work, we want to see, as some of you might have heard of it, COVID, the respiration rate, pattern, the depth of respiration, everything is highly related to the COVID. And this respiration is really different than the other respiratory illnesses. So it has this unique pattern. We want to see if we can make a sensor that's really going to be very low cost, like $15, $30, and if you can largely deploy it, ingress and egress areas and open areas, if you can get the person, like screening basically, screen a prognosis for the COVID-19. We have a lot of AI signal processing and a lot of things are here, but as I said, to respect the time, I will skip going next one. The next one is the gesture. The gesture recognition, the idea is this: Google has already did a lot of work using the radar, millimeter wave radar, but it's costly and expensive. We have a very simple light sensor and a full light source and light sensor, which is called photodetector. We do different gestures, 8 different gestures, and we got the measurements. The objective is really doing non-contact, especially nowadays, non-contact can be very useful for the COVID cases and for the machine type communication and for the human computer interaction, HCI. Next one, glucose sensor. We haven't done anything on human yet because this signal has to go through the skin and reflect back. But we have done with the solution, glucose solution. We got promising results and being published. And we are hopeful that we will start a funded research on these ideas as well. This is a very recent results. We are showing not all the wavelengths, but really some part of infrared wavelengths around 1200. We can see the difference between the water and glucose. And this difference is really critical for us to do the glucose sensing. All right, the next one is recently patented idea. It's really super simple. The classic speed detection and the ranging is using radar. What we have come up with this is that daytime running lights are always there. All the vehicles are having daytime running lights, even during the day. And these are really reducing the accident rate by 28%. The DOT has shown based on their statistics. So if we said if the daytime runnings are always there, why not putting a light sensor, or what's also called photodetector, next to the roadside, and to see as the car is passing by, from the intensity variation, can we get the speed of the car? And we did it, we did simulations and we did measurements. The initial results are promising, and our patent got recently funded, granted by the US PTO, or Patent and Trademark Office. Okay, one final one, occupancy estimation. As people walking around the room, the light reflections are gonna show the different number of people randomly walking inside the room, how the light reflections, ambient light, can be used to see how many people are inside the room. This can be really a very effective method for the HVAC actually. If no people are there, you can change your HVAC and all the conditions on that. One final thing I have is the do-it-yourself kit is an outreach effort with it. It has been massively successful outreach effort. What we did is really simple. We create a toolbox. We put amplifier, solar panel, and speaker, and 2 battery sources. This is the final setup. The students put this whole setup in their phone. They play a music file, and this light is flickering. It's all analog. There is nothing really digital, no coding, nothing. This light is flickering, and the solar panel is catching these flickering, so amplitude variations. And those are sending to the receiver, and we send the data. We send basically audio signal up to 7 meters inside the room. And the total cost for this kit is $30, around $30. And EC has funded these efforts. We have used in numerous efforts. The feedback was phenomenal. So they really loved it. And we have recently published in Transactional Education this idea, and we got very positive feedback. So I appreciate it. I definitely was not able to put all the list of collaborators, and want to thanks for all of them and all this work. And these are some of our, not some of our, all members basically get shown in here, and I appreciate our alumni and the collaborators, and I want to thanks for the supporters who providing support to us. Thank you. I hope I was not over time too much.
It's all good. Thank you very much. Applauding for everyone here. I'm glad that you all were able to come today. I do have time for a question if someone in the audience.
Sure, I have time, please.
Just unmute yourself. I'll pause for a minute and let you ask questions.
Can I ask a question?
Absolutely.
Sure.
So it was really interesting. So I'm just wondering what like the material that you use for like the different sensors, either like, you know, glucose sensors or like those like gesture sensors. What are the material that you use to fabricate those devices?
That's a good question. The sensors, the light sensors we are getting is just giving us intensity values for them. And we got most of our sensor from Tor Labs, but I have never really looked at the material. We look at the area size is super critical for us, and how big is the area. That's the important, but the material I have never looked at it. But I can really find that information right after our talk very quickly.
Mm-hmm.
Sorry about that.
Thank you. Oh, no problem.
Sure. Any other questions?
I think we have a number of CEAT scholars that have been on the call as well. We've had some undergraduate students that have dialed in. I have a question, Sabit. You've got a lot that's really going on, and kind of what would be, where do you see your progress in the next 5 years in terms of where you want to be? I think 5G will likely be fully operational in the US by then. I mean, and the US is a little behind, I think. How do we catch up? How can we?
To give the numbers, the US is really 6 months to 1 year behind, to be honest, on the 5G. And Qualcomm is investing a lot, especially because of the fights between Qualcomm and Apple. We were really lagging behind, but now they have a good agreement. So my goal is really, yes, wireless communication will be there, and 5G and 6G will be our primary goal. Terahertz communication, actually, we have got good momentum with our recent MRI, NSF grant, and with the Twister team. That's one thing we will be really heavily investing on it, using both time domain spectroscopy and the CW systems, and to do terahertz communication system. That's one thing we will be working on it a lot, because millimeter wave is kind of matured compared to the terahertz, I will say. And the other thing that I will be mostly investing is the light wave sensor. It's really low cost, and the recent DARPA YF Young Faculty Award, their second topic is very similar to this idea. They want a sensor to be designed, any medium do you want to use it, light, camera, RF, doesn't matter. They want to see if you can detect at a stand of distance people COVID, to see any COVID or flu or anything, so that you can tell the people, hey, don't get inside. It's basically in the ingress entrance of the buildings. So lightweight sensing will be number one thing. And I mean, equally actually, and terahertz communication. These two will be my really next 5 years effort that we'll be investing on.
I know some faculty at Northeastern in electrical and computer engineering had developed a sensor that could sense COVID basically on the breath almost instantly. Are you aware of that activity?
They're using, if I know MIT team, they're working a lot on it, and they are mostly using the RF. So RF, the first invention for the RF using radio radar for the respiration and breathing has been done 1987. And they found it as a lie detector, actually. As the person is basically talking, the heart rate is getting higher, and they said this guy is lying. Basically, that's how they worked on it. And since then, people have been working on it. But there are two concerns with the radio frequency. People don't want to put in the hospitals. EMI is a big, because it can really impact the life. saving medical equipment, and EMI is there. We like it or not, but it's there. And the other thing is that is costly, and directivity is really hard as more people are coming, as becoming another challenge, and spectrum crowding is another challenge. In short, although it has been there last 30 years, there is no product out there really saying we can use it. So in that regard, in this regard, we believe that the light may be a good really opportunity to track it, because it's easier to beam, change the beam, and it's very low cost, and we can use different color of the spectrum to detect it. So
very good. All right. Hey, well, again, I want to thank Dr. Hamadi and Dr. Ekin for being here this afternoon, and thank you to the audience for your attendance, and I hope that you benefited from it. And our next seminar will be Friday, November 6th. And so watch for some announcements regarding that. We have we have 3 more sessions this semester, and I do value your input, things that you might recommend to me to help make this a better experience for the faculty and for the college. So please feel free to share those ideas with me now, or you can just send me an email and we can visit offline separately. So, all right.
awesome. Thank you.
Very good.
Thank you.
Thank you. You guys have a great rest of your afternoon and a good weekend.
You too.
Thank you.
Thanks.
All right. Bye, everyone.
Bye.